All right, we good to go?
Yep.
All right. Welcome back, folks. Today's part 2 of motion planning, and I want to remind you where we left off. So basically, the problem we're talking about for this week has been to try to find trajectories through space, typically parameterized in the joint angles of the robot, in order to accomplish more complicated tasks in potentially more cluttered environments, or to accomplish them more efficiently, more quickly, right? And I tried to argue last time that actually, if you understand inverse kinematics in its full generality, then actually that's a lot of the motion planning problem. That what we want is the language to be able to specify not only end effector constraints and the like, but also joint limits, collision avoidance, all these different things. And if you solve the inverse kinematics problem well, then you're most of the way there. And then I tried to give this specific example where solving inverse kinematics problems independently was not going to find a solution that would accomplish the task. That actually, even solving two inverse kinematics problems at once to find a particular grasp on the object that satisfies both the collision requirements, collision avoidance requirements in order to pick up the mug, but also to set it back down. That can actually dominate your decision about where to grasp the mug. Okay, so there is motion planning happening here to connect those initial pose and the final pose with a trajectory that moves the robot. But actually, the first step is just solving two inverse kinematics problems simultaneously, where the constraint that linked them together was just the constraint that said the mug has to be in the same relative position relative to the hand in the initial pose and the final pose, and then the initial mug position is given, the final one is desired in the sink, right? You'd think I've worked on dish loading enough that I would stop saying sink and dish rack, but okay, in the dish rack. Good. So I apologize that I ended up finishing that GUI, for you. I hope some of you played with it afterwards, but I've added more to it. So let me pull it up now and make sure that you understand the tool that I was trying to give you last time. So I can flip to my little Jupyter notebook here, and you'll see my EWA. And there were a couple different interactive inverse kinematics widgets that I gave you here in the notebook. The simplest one, and they run through this just a few lines of code. There's some setup, of course, and some GUI stuff, but basically I just make an inverse kinematics problem. I added a position constraint saying that the gripper pose was where the sliders tell me to be. That's a position and an orientation constraint. And then the only other thing I did was I added a quadratic cost to say I'm close, just like I showed in the Atlas slide, I'm close to the nominal configuration. And this gives us effectively the same kind of interface we had with the differential inverse kinematics one. But instead of solving it incrementally and just moving using the Jacobian, this is actually solving the global problem at each frame. And the fact that it's doing that interactively is kind of cool, right? So I can move my sliders around and it's giving solutions. There's a couple things you'll see in this one that you won't see in the original version. It'll occasionally jump between solutions. If I were to get to a place where you'll see it more in my other examples, but we'll see that was a good example right there. It just jumped, right? There's really, we're relying on the solver finding some solution in a big, complicated nonlinear optimization problem. And continuity between two different calls when I move my sliders around is not guaranteed. There's nothing I'm doing to guarantee that. All that we're doing is putting ourselves in a different set of constraints, saying the end effector has to be here, watching the optimization solve, and it just happened to find a different solution this time. It went down a slightly different hill. It probably means we're on the verge of some, right near some cusp in the landscape. Okay. So you might want to, yeah, it's a good spot right there, huh? But so you might not want to use this as by just solving inverse kinematics problems this way independently as you go. That's why we prefer some of the Jacobian or trajectory optimization. But the fact that you can do this global solution at interactive rates is super cool. Okay. This is now, richer than the Jacobian-based control because we can add complex nonlinear constraints. So just to add some sort of obstacle in there. And then this is exactly the same optimization I had before with the addition of an add minimum distance constraint, just saying that the collision geometry on my robot and the collision geometry in the world have to stay at least 1 millimeter apart. I guess I could have given it a little bit more space than that, but otherwise it's exactly the same. And now, it'll do its best to avoid, this is something we didn't do in the Jacobian based, right? But it'll do its best to reach around specifying a target. But if I push it, at some point it'll start saying it's in IK failed over here. It might actually pop to the other side. There you go, right? If I went far enough, but we're still starting it with an initial guess that's on the right side of the pole. So it's harder for it to find a solution over there. If I was, in this part of the workspace, then I would set my initial guess differently to my optimization. I've just set the initial guess originally, from the comfortable position always in this particular optimization.
Out of curiosity, can the solvers in Drake handle invalid initial guesses?
Yep. Yep, that should be fine. So this is SNOPT is actually pretty robust. In fact, the fact that it's sometimes reporting failed, but still giving a best effort solution is actually a very nice property, right? So it's going to give you the best one it can, satisfying the constraints with a minimal violation, even when you give it completely infeasible. And if you start it with an initial guess that's infeasible, it'll try to walk back into feasibility. There's absolutely, in fact, it's almost a non-starter if you require feasibility, right? That would be a pretty hard assumption.
That's what I remember from one class I took, is that getting the first initial feasible solution is the hardest part of the rest of it. So
it can be, yeah. Well, we're going to look at some of the landscapes, pretty carefully and try to see if we can understand that. And then we talked about trying to, so in both of those examples I've showed you so far, I put a full 6 degree of freedom constraint on the end effector, and it was pulling that around. But if you don't have to do that, you often don't, then you should try to write the minimal possible constraint on your end effectors or whatever, to give your robot, your solver and your robot, the most flexibility possible to accomplish the task. So this was just the example of the cylinder. Oops, I forgot to clear my other thing out. So here's the cylinder, and now I've put the slider on the cylinder so I can move the cylinder around, and it's going to grab the cylinder, right? But it doesn't, there's nothing. So these are exactly the constraints we talked about last time, where I said the position, it turns out it was the z-axis, not the y-axis. On above, we were wrong about the y versus z, but I just said there's a point just above the hand and just below the hand that are in the zero frame of the cylinder, and they stay inside the cylinder. And that gives me, with just these two position constraints, gives me all the things I want. But I can move this around. It does nothing until it gets to the end of the pole, and then it tracks it. I guess it's easier on the other direction where I. Okay, so you're going to see I'm going to try to visualize all the constraints in a minute here, and you're going to see that giving yourself that flexibility is going to dramatically simplify the problem, especially for a sampling-based approach that we'll talk about. But even for optimization, you want to leave as much room for the optimizer to satisfy other constraints, like where I set the mug down at the same time. So write your constraints in the minimal way. And that's a nice, the fact that there's like this nice language on top of the kinematics that allows you to do that, I think is very cool. Just because I'm immature or something, I realized that I had basically made an interface where you can antagonize your robot. So now the robot's not grabbing it, but you basically have a stick, right? That you can kind of attack your robot and it has to dodge. You can make your robot do the limbo and stuff. Whoa. So I guess that was a bad one. Go back up here. Got a little lag on my interface. Oh, good. Anyways, it's trying to solve this global problem, and it's pretty good at it actually. If you play around, and I hope you do it on your own time, and you've got the interface there, it's pretty darn good at dodging the constraint. Of course, it has to sometimes flip to the other side, and the real robot can't just move through the other side. This is solving as if it was unconstrained in time, right? It's just solving the instantaneous inverse kinematics problem. Good. So the picture that that I'm trying to give you here is that kinematic trajectory optimization now or rather, maybe I should put the emphasis on trajectory optimization. Is really, in many ways, I think the important part is that you're just trying to solve many inverse kinematics problems simultaneously. So we talked about the final pose and the initial pose, and the full trajectory optimization problem would just be to solve for many of them that are somehow linked through time, right? So the picture I want you to have in your head is that I have some configuration space of the robot. We're going to draw some, we're going to visualize some that are in 3D, but imagine I've got some high dimensional one. I'll just draw two of the coordinates, the joint angles, right? And my goals, for instance, being aligned with the cylinder, represent some regions here, which I've tried to color green fairly consistently. This is somehow like regions of space for which I'm satisfying the goal. If I specify a particular grasp with a previous grasp planning algorithm and just say you must be in this, then that would be equivalent to just setting a point in this space. Okay, unless you have redundant degrees of freedom, but it's almost a point in this space. Okay, and if you can somehow be more expressive with your specification, then you can turn that into a bigger region or a higher dimensional object. And then we have other things like the pole that I was antagonizing the robot with that are somehow providing constraints of regions of places you can't go. And you have some initial position for the robot, and all we're trying to do is find a series of points that somehow get me into the goal region, where each of these points is avoiding the constraints. And it really can be as simple as solving individual inverse kinematics problems, where you'd like to have some link between them saying they're not too far apart, or we talked about last time, spline piecewise polynomials, or cube or B splines. Now, the trajectory optimization approach of solving all of these things simultaneously, that sounds heavy-handed, right? To make a program where I've taken this thing where I'm solving min over q, and I'm suddenly trying to solve a much bigger problem with many more decision variables. Q at time 0, Q at time 1, Q at time n for each I, I've got some constraints. But actually, the solvers scale very well in the number of decision variables. These solvers tend to. And that's a fundamental idea here, which is that the trajectory optimization approach is fundamentally kind of a gradient-based, a local-based approach, where you choose some initial guess at your Qs, and you try to improve that iteratively. And in higher dimensions, it costs you a little bit more to compute the gradient. You might have more constraints that you have to evaluate. That'll slow you down. But there's not some exponential complexity hiding there, or about the fact that you have more Qs. You really, even if you have thousands of decision variables, you can just decide on compute the gradient and walk downhill. You might have more local minima or other things, but the trajectory optimization approach actually scales very, very well. Thousands of decision variables are routine.
You scroll down a bit, Russ.
We can't see.
Got it. Thank you. Okay, so the problem with the trajectory optimization approach is that it's not guaranteed to find you a solution. By virtue, the thing that makes it scale wonderfully, by being this local method of taking an initial guess and then just trying to locally improve it by walking down trying to minimize the constraints a little, reduce the constraint violation and minimize the objective, is also the thing that will cause it to get trapped in local minima. So to give maybe some evil-looking versions of that same motion planning problem, and the problems that we're going to try to work around with some other techniques here, if I take my same space and I had some initial state here and some nice big well-defined target region over here, but I had some, I don't know, some evil, I think they're not normally this bad, but actually I'll show you some that are pretty bad, right? Some strange looking obstacles in my joint space. Then you might find that if your initial guess is a bunch of trajectories like this, right? The system, this is the easy one, but there are some even simpler ones that are just as bad, okay? Is that my initial solution here, in order to find the solution I really want, which is some path around the side here, it has to violate the constraints more in order to maybe even bring more points into violation on the path to going from this solution over to this solution. So it's very unlikely to do that. You'd have to get very lucky with a gradient step that happen to bounce over. And basically, if you have an initial guess that's here, you'll never find the path that goes around there. This can happen in more, it doesn't have to be that adversarial, I guess, to have this happen. Imagine I just have an initial state here, some goal state over here, even just a box, okay, an axis aligned box. Right, if I have some initial trajectory like this, right? Then if you think about what the constraints that we're writing on this object, each of these points, by virtue of saying the minimum distance between from this, of the robot between this point and being in the obstacle, it's going to be trying to pull itself out of this, out of collision, and this one will similarly be pulling itself out of collision. But the constraints that are trying to keep continuity are actually, are pulling maybe in the other direction. The fact that it's got to stay close to the next point in the trajectory. And there's nothing that this thing's going to do. There's no local information in my cartoon two-dimensional space here that's going to ever take that out of collision, right? So sometimes the gradients will just not give you the information you'd like them to. And we'll come back to the fact, but the fact that we are solving all of those points as a single optimization is both wonderful in the sense that we can write nice constraints on, they can link the optimizations in important ways, but it's also the thing that's going to ultimately cause this to be maybe not the most preferred method of choice. It's a hard optimization to solve, problem to solve. Now, do you understand why I'm calling these local minima, right? So it's a little harder to think about with constraints than controls, but ultimately we have some decision variables. If I've got some complicated landscape. Would be my objective function, for instance. But if I added on a local minima, I think people have a sense for if I started here and my solver finds this, then it's not finding the optimal solution. But it's even worse if I do, subject to some g of x greater than or equal to 0, for instance, and maybe that's like this region here is the region where I won't accept any solutions that are in penetration, for instance. That might just put this rift in the middle of my optimization problem, where the system, if it starts with a guess over here, will hit up against that constraint, and will not, in an attempt to not violate the constraint, will never jump over to the other solution, over to this solution, right? So the constraints can cause local minima in a gradient-based optimization just as well as a objective that's non-convex. Okay, so the alternative approach that is dominant in the field is a sampling-based approach. And sampling, well, we'll see, but sampling, you wouldn't expect to scale as well to high dimensions, but it does surprisingly well. Okay. And the picture I want you to have in your head again here is in my joint coordinates, even with some initial state, some final state, some reasonable acceptable goals, and a bunch of obstacles. Rather than find an entire path all at once, one shot with an optimization, we're going to just start sampling. Okay, so we're going to just pick a point at random in the world. Okay, pick another point at random in the world. Just start adding points into our. I'm going to make this precise in a second. We're going to just start adding points. If we add a point that's close to another point, then we'll add an edge between those 2 points. If we add a point that's inside the obstacle region, we'll discard it. Just reject that sample and keep sampling, just trying to find another sample. Okay. And eventually, we'll have made interesting connections. Our very sparse graph will eventually fill in, and we're gonna at some point find a path that will take us all the way to the goal. This one now, you can imagine if I had my adversarial obstacle like this, right? It will still eventually, it might take longer to find a longer path, but it will still eventually find a path that will walk its way all the way around. It doesn't just stop when the trajectory gradients have no information. It will eventually find its way around. So this this version that I've talked about here real quick is called the probabilistic roadmap. And let me actually show you the algorithm in words here. Okay, it's one of the most famous algorithms in motion planning. There are various versions of it. The first one came out, it was by Nancy Amato, but there's many beautiful and important refinements to it. And the roadmap is constructed. You'll see why it's called the roadmap in just a second here. But so you're going to put a total number of points on your map. You're going to define some metric for how many you're willing to connect to. Okay, like how this is in terms of neighbors. You might have a threshold in terms of distance instead. That's the way I drew it. You start with an empty set of vertices and an empty set of edges. You pick a random configuration from your configuration space. Q in all the motion planning literature is basically the subset of the joint space, which satisfies your constraints. And most of the time, they're talking just about collision constraints. Okay. You check it. You find one that's collision free. Add it to your list of vertices, and then find your closest neighbors. If they're less than some distance, you add that as an edge. Okay. And the picture that you'll see everywhere are these things that look like this. Basically what I drew here. Okay. But the nice thing is it's not just a single path that it solves for, it's a roadmap, right? So it comes out as a fully connected graph. No, sorry, I didn't mean to say fully connected, a densely connected graph. Okay, there's many nodes that are connecting many other nodes. And then when it's time to actually go and plan with this, and you've got some initial condition, then you go into the query mode, where you just have your initial condition. You just have to connect to any place on your existing roadmap. You can take your goal state, in the case of being a point here, connect to any place on the roadmap. And now you have a shortest path problem on the graph to just find your path. The beautiful thing about this version of the algorithm is that if I've done a lot of work to figure out my roadmap, and now I'm going to continue to operate in the same environments, I'm going to take another motion or whatever, then I could just have a new goal, connect back up, and I can use the same roadmap for many queries. Right? It's a very nice, efficient way to sort of figure out your space once and use it many, many times. In fact, people have capitalized on this. This is like a super cool idea where they've done the PRM basically on an FPGA, hardware accelerated the heck out of it, because there's a paper by Nancy Amato who said saying that PRMs are embarrassingly parallel. So these folks are adding collision geometry from their connect, so that if a human, for instance, walks into the operating space of the robot, or the boxes move, they're just updating their existing map, truncating some edges, but they can do online, on the fly, remapping through the graph. Good. Yeah. So Rebecca asked about collision checking, and the picture that I drew, the sketch that I drew, and the one in figure 7.4. So typically, when you add an edge, you will actually, even if the graph itself is relatively sparse, you will typically do many fine samples along the edge just to make sure that it's not in collision. Some people do, like we talked about at the end last time, some people will try to do more complicated things, like taking the convex hull of their collision geometry across those points and trying to give some sort of guarantee. But far and away, the most common thing would be to just sample a lot along every edge before you're willing to add the edge. So this was the 2016 paper that they sent to RSS, sort of with the idea, but now they're a company that's got lots of customers and funding, and their robots move fast, and they have, I guess, probably nicer boxes. But it's a pretty cool technology, right? Yes. Okay, so the question I want to stop and think about, you will find people that will tell you many more details about the particular PRM algorithm, and we'll talk a little bit more about some of its key properties. But first, I just want to challenge whether we actually need it. Okay, so what do the constraints actually look like on our robot? There's a couple different geometries. I don't know if you've noticed that the URDF files that we have for the EWA have different names attached to them, typically defining what the collision geometry is. So there's like EWA 14 no collision, there's EWA 14 box or EWA 7 box collision, and there's EWA 14 sphere collisions, and there's EWA 14 elbow sphere collisions, and this is what they roughly look like. So Drake Visualizer just makes it super easy to see the collision geometry, so that's why these are just still images. But this is the box one, which actually we never use. I think Tomas actually made this one last year for us just to have it, and maybe it's the most conservative one and very simple collision geometry. We tend to use, our collision checking is pretty fast on spheres, so we tend to use this one that looks like it got attacked by that. Do you guys remember in The Incredibles when that gun came out and just, it sort of looks like that. Yeah, but these are the sphere collision geometries, and this is maybe not typical. This is because the EWA is this very shapely robot, and so it requires creativity in terms of the collision geometry. I think probably most of the world, like a UR5 or UR10, whatever, you just put a cylinder and you're good. This is us getting creative to accommodate the strange geometry of the robot. And this one is sort of a compromise in between, where the things you tend to hit are your elbows and your wrists and stuff like that, because you pay a little bit of a price every time you add some more spheres. So we've left some of them off in this one. So what's the thing you have to pay? Okay, so every one of these queries about saying, am I in collision or not, is typically going into a collision engine, which is running a pretty sophisticated computational geometry backend. And intellectually, it's basically computing from the, is every possible collision geometry pair in penetration. The way it actually does that is, of course, it doesn't actually try to check every single one. Well, it does, but there's algorithms that make that pretty efficient. So in particular, you'll take any of your collision geometry, you typically come up with an axis-aligned bounding box for it. And then axis-aligned bounding boxes are super fast to check, and there's good data structures and good algorithms to rule out any other more detailed checks. So spheres are really easy to check, right? Especially sphere-on-sphere collisions. Boxes are pretty easy to check. So you play this game of the complexity of your collision geometry with the cost of doing that collision check, right? And conservatism, this is gonna, there are places that the robot might not be able to go because the collision geometry is bigger than the robot here. It might be that, sorry, it might be that there might be something where the robot could have gone, but the collision geometry told it no because of that inefficiency in space, but it's a faster collision query. So it's a matter of balancing those two. Okay, so I want to sort of challenge whether, are we in this like crazy configuration space motion planning problem or not? Yeah, that's true. You can definitely parallelize your collision queries. All right, so I made this this GUI. Hopefully, it's loading up for you too. Yeah, here it is. Okay. There should be one more here. Here it is. Okay. So I put a cupboard in this space, and it's in your notebook if you care to run it, but I put a cupboard in the space, and I put a goal ball here in the space, and I basically just said, let's solve a problem. This is now the planar EWA, so it's only got the 3 degrees of freedom, so it's a 3D space that I can visualize. And this is a more constrained kind of manipulation problem where you have to reach in right inside this constraint. Okay, and then I put together this I sampled the many different joint configurations. So this is a 3D problem. This is a different visualization now, but the x-axis corresponds to joint 0, the y-axis with joint 1, the z-axis with joint 2. Okay, if you you can see there's a bunch of things visualized here. So let me turn off the collision. That's a noisy one. Okay, what are we looking at here? So this is my initial guess. This is now, by having turned off the collision constraint, I basically pretending that the cupboard isn't there. Okay, this is my initial guess. Some just default comfortable configuration of the robot, Q0. Okay. The optimal solution that it found is actually, it's got to be inside my green region. It's hiding down here. Okay, there it is. That's my optimal solution. The green region is the feasible region as defined by my loose constraints, saying all that matters to me is that the ball is at some point in the gripper, but the orientation is, well, in this case, it's a planar robot, so it can only go like this. Okay. So the green region are all of the joint configurations that satisfy that constraint inside the joint limits. Now, do you see the geometry of that? It's kind of cool. I just did this by sampling a bunch of times, calling a marching cubes algorithm to fill it out and turn it into a mesh. And now you can like look down your constraint tube if you care. But okay, so this is roughly some geometric ring, okay, but it's truncated by the joint limits. What does that correspond to physically on the robot? This is joint axis 0, 1, 2, which is 0, 1, 2. Or rather, I should have pointed over here. 0, 1, 2. Right? What are the different solutions that would accomplish that? There's a whole manifold of solutions that can walk the elbow around, right? But it is a manifold. It's got this interesting topology, right? The reason I've given it the reason it has volume is because I said that show me the constraint tolerance up to some limit. So if it was actually, if I set that limit to be 0, then it would be hard to compute a mesh and draw it. But it would be just actually a ring of solutions. Okay, but that's the manifold. I'm not a planar EWA, but it's the manifold of my elbow coming in and out and still staying in the same configuration of with the ball inside the wrist. Okay, so that's pretty cool. Now, what does the cupboard do to me? Right, that's a big messy one. Now, over here, there's many joint angles where it has no impact whatsoever. Okay, the red, I'm sorry that it's these are the walls of it, but it's hard. The interior of here is off limits. I'm just drawing where the constraint turns on and turns off. So how does the robot get into the configuration it did? Well, the inverse kinematics had to find a little path right around this corner. There's a little nook here, right? Where if I look down there, there's a little nook where I've got feasible solutions and I can reach inside, but it's a big robot. In fact, I even had to turn the hand. Normally the planar gripper has the hand in this plane, but I rotated it. I rolled it 90 degrees just so you could see the channel. It actually did find a solution when the hand was the other orientation, but it was numerically hard to see, okay? Anyways, so the motion plan, or the inverse kinematics algorithm has to escape this red region of terror, get into the green region, and then amongst all those solutions, be as close as possible to my comfortable region, which is this point up here. And the nonlinear solver did that. They pulled it out, found this nice little point down here. Yeah, pretty cool. So the question is, you can imagine more terrible geometric configurations for your robot than that, but maybe. I mean, I actually don't think there are cases in motion planning where the problem really is this massive geometric puzzle, but you know, I don't know if manipulation is really living in that space most of the time. I don't know. I'm curious what people think about that. I think the reason that the sample-based motion planning is I think there's other reasons why the sample-based motion planning is so popular and so effective. Right? I don't know that it's really this rat's nest of obstacles. Right? In the extreme, let me just, yeah, so in the extreme, there's a, right, this is like the geometric puzzle. This is the motion planning problem. I thought about putting Dale's piano in there too, but you know, there are really geometric puzzles that you can try to solve with these type of algorithms, right? So like, I don't think that's what our arms are living in most of the time, right? So, yeah. So what are the, well, okay, so that's just to set the stage of are we really in the super hard algorithm space, okay? Let me tell you quickly about the other major contender in the space. So the probabilistic roadmap was algorithm number 1. Algorithm number 2, and they're all mostly, oh, sorry. The visualization on the right shows the joint space for a subset of the 7 joints on the KUKA, correct. So the planar IWA, it's actually 2, 4, and 6, but yeah, basically what Terry said. Yes. So I've welded the other ones that would move the robot out of plane, and we just call that our planar IWA. Is the visualization counting for self-collision? It actually should be, yes. Well, so the default collision constraints in Drake will ignore self-collisions between adjacent links, and then if it will show a collision for when the wrist, for instance, would intersect with the base, right? But not, you know, this link intersecting with this link. We rely on joint limits to do that. Otherwise, you'd be checking collisions and fighting those all the time. Awesome question. Okay. Yeah. So the probabilistic roadmap is an extremely useful algorithm. Maybe if you want to knock it, I think the idea of just sampling uniformly in over your entire configuration space, it's a little bit harder to think about it as a goal-directed, or to put in a bias that's sort of pulling you specifically towards a goal, or specifically towards the initial conditions. There's a slightly different version of this, the RRT, hugely successful algorithm. In underactuated, we talk about this more because it's more useful in the dynamics case. So there's other reasons why RRTs are good, but the algorithm is almost as simple, but we think of it as growing a tree instead of growing a roadmap. Okay, so think of it as a single query planning algorithm, where you start with some initial state. Every time you have some initial tree now. Okay. You pick some point at random in your state space. You find the closest point in your existing tree. The initial tree is just the single point. But each time you find the closest point in your existing tree, and then you grow your tree a little bit towards that random point. Okay, and instead of growing a roadmap sort of uniformly over the state space, this one is really trying to grow out from an initial condition, and potentially you can do it backwards also from the goal, and grow out from the goal, and then try to find these trees that match. And it can be a little bit more directed in its search to the regions of interest. These problems, both RRT and PRM, this is the canonical bug trap problem, where the initial pose was somewhere in here, the target was over here. And you would say this is like extremely hard for the motion planning algorithms, because they have to sample their way down a very long tunnel. But I actually think this is the success story of the randomized motion planning, is the fact that if you run this long enough, it will eventually find a path if it exists. And we'll talk about exactly that statement of probabilistic completeness. Okay, And they really do solve, like that, those two, the geometric puzzle kind of problem. Yeah, so when James Kuffner and Steve Lavelle worked on this algorithm together, and they were, making these kind of geometric puzzles, but James was also working on humanoids at the time, and it was super surprising that you could, to me, that you would take a sampling-based algorithm, which you would expect to sort of, kind of give out in higher dimensional spaces, because sampling in many dimensions should take a long time, right? But he was showing these pretty impressive plans coming out for big, complicated robots like this humanoid robot. This one had its feet bolted to the ground and was staying inside the ZMP constraints, and there, but it's shockingly good. Okay. Now, the lesson from the RRT is that that's super simple algorithm. Let me pause this for a second. The super simple algorithm is more clever than it lets on. Okay, this idea that you pick a point at random in state space, you find the closest point on the tree, and you grow. That sounds like, oh, okay, yeah, but I could have done any number of different things and had a successful algorithm. It's not always the case, right? So for instance, if you did a similar sounding algorithm that just basically you have an existing tree, pick a random point on my tree and grow it in a random direction, that will give you this, if you run this for many, many times, you'll end up with a rat's nest of a tree on top of your initial sort of sample point. Okay, so there's something very clever about picking a point at random in space and using that as a heuristic to pull your tree outwards in space. And the interpretation here is cool, right? So do people know what Voronoi regions are? So this is just now a tree in progress, okay? And I've drawn in the Voronoi regions. So each region here is the set of points that are closest in a Euclidean sense to this point. And for every point, I've drawn the region of all the points that are in distance closest to this point, okay? So everything in this cell, if the RRT were to sample in that cell, in its sampling state, then it will expand that node, right? Similarly, if it, over here, it'll expand from this node. Now, the beautiful thing, okay, you see in practice that these RRTs tend to kind of explore space very quickly, rapidly exploring, okay, random trees. And you can understand that through this lens of the Voronoi diagrams. They call it the Voronoi bias. So, they grow out and fill available space quickly. And then the really amazing thing that makes them, find that solve even the bug trap problem is that they will then, after they've filled out the space, they will go back and fill in the details of the smaller regions. Now that sounds sort of like I'm giving it, personifying it in some weird way, but let's just think about it. So the probability of sampling, if I just pulling samples from a uniform distribution over the workspace, the probability of sampling something from this region is much, much higher than the probability of sampling in this region, right? So in fact, the likelihood, the probability of extending the nodes here is proportional to the volume, or the volume of their Voronoi region. So it actually has a bias just by having the naive sampling in this extend operation, where it will sample more likely from the big regions. It is more likely to expand into the available regions. And then, as those big regions aren't big anymore, then it's just as likely to sample from the smaller regions here. And it will sort of, probabilistically target any space that it hasn't crawled through yet and eventually cover the space, okay? In these sort of simple, unconstrained, so I don't have any dynamic constraints, only collision constraints, then in fact, the final distribution of points on your tree will converge to your sampling distribution, right? So eventually you expect this thing to converge to the, points that are uniform everywhere in space, even though they might have had to go through narrow passages to get there. If people haven't seen RRTs before, that's a lot to grok, you know, so ask questions. So it doesn't explicitly say, the sampling algorithm is exactly what I wrote on the other slide here. Sample at random. So for instance, just uniform in the space, and then find the closest point on the tree and grow. That algorithm, I'm not adding embellishments to that algorithm. That's the simple, super simple type it in algorithm. But by virtue of finding the closest point on the tree, which is a nearest neighbor calculation, you have implemented that Voronoi heuristic, basically, just by doing the nearest neighbor queries. So the Voronoi stuff happens magically without ever computing Voronoi regions. Right? Actually, making that video was like way slower than running an RRT, because actually having to compute all these regions and all the different cells is computationally expensive. And it just does it implicitly by picking a point and just finding the closest point. It's doing that computation. Okay, so there's a world of sample-based motion planning out there. OMPL is maybe the most famous one, and if you've heard of Move It uses OMPL as a backend. Ross has got OMPL stacks inside it. This is actually one of the older videos from OMPL, but there's a rich library, open source, very good, very useful. Lots of people use Drake and OMPL together. You can just Google if you want to find it. Certainly, the one I quickly Googled, that there was C++ examples, thanks to Dexi for putting those up. But you should be able to do it just fine with the Python bindings. You pay some performance hit, but the only reason I didn't give you an example to work on today is that installing it on Colab they don't have pre-compiled binaries. I tested, but decided that the compile time on Colab was not something you guys want to deal with. And I didn't want to package it last night. Okay, so, but it's interesting and informative to sort of go through and look at the planners that are available, right? They really do have a bunch of versions and variants of this PRM. These are under the multi-query planner algorithms, right? There are a lot of different variations. I'll tell you what the star means in a second. And then the RRT is really the other, I think, dominant class of algorithms. There are a few others that are worth understanding. For the most part, those just try to find any path, and there's some set of them that try to actually find the optimal path. Okay. I want to think for a minute with you about what are the differences between sampling and trajectory optimization, okay? Well, actually, let me tell you one, let's do one more thing that this video was leading me up to. So what is the configuration space that we should be sampling of with these sample-based planners, okay? So in a lot of the examples that people use in motion planning, it really is just my robot trying to move through the world, and not running into things. But in a lot of our manipulation problems, right, we actually have both the robot and the objects that we try to manipulate. And there's a super interesting question about whether we should include the object's configuration in our sample-based planning. What do people think? If I'm trying to move a mug from one place to the other, is the orientation of the mug, right, the position and orientation of the mug, part of my sampling? It almost never is, okay? There are cases where people do. In fact, the example I showed you of the task and motion planning is exactly where people build up to trying to use these methods to do both. But there's a couple things, there are places where you can put these two together. But I actually think it's easier to do this with an optimization-based planner than with a sampling-based planner. So let's just think a little bit about why that might be. So let me give you this simple example here, which looks like I forgot to autoplay, of just trying to move the mug from that side to this side, okay? That's an optimization-based planner where it's making a single plan that does the entire motion, including grabbing the mug. The configuration space of the mug is part of the optimization, okay? And it solves the whole thing simultaneously. So how do we do that? In trajectory optimization, we can do, for instance, minimize over Q robot. Let me just not write robot a bunch of times, but I'll use the notation dot here to the entire trajectory of the robot. Okay, and it's actually not that much harder to add one more decision variable here, which for instance could be the pose of the object relative to the gripper. We could write it in quaternions. We could do it in roll pitch yaw XYZ. You probably wouldn't do it in the full 4x4 matrix, but let's just add those as decision variables. And then, so we have for all ik of Q robot I, some set of constraints. We could say just for samples I, let's say between 5 and 15 or something like this, we'll have the first 5 samples where the position of the mug is just irrelevant to the task, okay? But in time between 5 and 15, we'll say that basically this xg is some constant, okay? It's our specified. We basically lock the hand relative to the mug, move it over, and then for time samples, 16 through the end, we leave the mug alone again. Okay, so by adding one additional set of variables, which again, these things scale actually pretty well with time, and defining the order a priori of when, which samples in my inverse kinematic solution have the mug attached to the hand and don't, then that's actually very easy to write those different optimization problems. And that's the ones, you'll see a lot of things that look like that as basic manipulation planners. Okay, so if you watch this very carefully, you'll see that the mug was sitting on the table, the inverse kinematics comes down, there's a little snap, it gets attached to the hand, right? And then you'll see it sort of snap off for the next, when it lets go, okay? There's no dynamics there. That's just saying that the mug was in its final target position at the end, and any tolerance from our solver left that little snap to happen. But these sort of equality constraints that are binding decision variables together, they're natural to express in trajectory optimization. It's a little less natural to express them in the sample-based motion planning. What we would tend to do instead in the sample-based motion planning is just plan 3 trajectories, one that gets me to the mug, a second one which is with the mug sort of constrained in the hand, and I'm avoiding collisions between the hand and the sink also, for instance, or the mug and the sink also. Solve a different motion planning problem for that, and then solve a third one. Okay, the independence of that is a relaxation. You know, sometimes you would like those to be coupled through the optimization, and you tend to separate them in the sample-based planning, which is both a strength and a weakness. Okay, so let's put head-to-head sample-based planning versus trajectory optimization. The local minima, we said, was the biggest problem with trajectory optimization. And then I tried to question, you know, are we actually in a space of terrible geometric constraints or not? And I think kind of, you know, sticking the hand in the shelf is a pretty hard one. But a lot of times where you've got just bins or something like this, or, you know, if we're robots preparing food in the kitchen, I don't know if collision, if it's not solving some geometric puzzle to do that. Okay, but there are some other sort of pros. Let me say a plus was a pro for a sample-based planner. Okay, one of the really nice things about the sample-based planner is that they do a lot of these hard problems, but they only require Boolean collision checks. You only have to ask your collision engine, here's a pose of my robot, you know, and all the objects. Is it in collision, true or false? And that's tends to be a faster. That's the place where collision engines have been optimized a priori for game engines and the like. So that's a big win to do that. If you compare that in trajectory optimization, we're actually computing distances between objects, sign distances, right? Our sign distance function. And even to do it well, we're doing gradients of those sign distance, which can be done pretty efficiently if you've computed the sign distance. Actually, the normal, it's not like you have to go into AutoDiff to do that. Most of the gradients are easy to carry around, but you do have to. It's more baggage to plumb through your simulator and everything like this. But I think the bigger one here is that you don't need to predetermine the number of points on your trajectory, okay? And you don't have to predetermine even the connections between these points. That's a big deal. There's something sort of fundamental when we write the optimization problems that I like to write, is that you've preordained some dimension in X, right? There's some dimension of X, and our solver doesn't like that to change. We're taking gradients, we're doing all these things, but it's always in a fixed dimension X. In practice, that means you've got some fixed number of samples that you're solving for IK. In the motion planning problem, it's not only that we don't need to do that, that we can be flexible about the number, but the fact that we've completely made each IK problem is independent. Right? By every sample is just a simple Boolean check. If we have joint limits and other things, those are checks. So you should think of each of these samples as solving one inverse kinematics problem by itself, okay? And the fact that we're solving them separately and then deferring the connectivity of them and the shortest path computation across them, all the constraints that go across them, we're deferring that to a second phase, right? That's a big, not only a computational simplification, but it fundamentally allows you you're parameterizing a bigger class of problems. right? So, so you can find solutions with arbitrary number of points that you can't find with a fixed a priori number of points. And even there are quirky local minima, like to even not say that this point must be related to this point in the optimization. If I had some initial guess that was like this, and then another point came along, the connectivity can just sort of change. I'm willing to go down this path instead of this path. That's something that the trajectory-based optimizers can't do. And I think that's the fundamental reason why these things become better. Good. QRobot desired, I think your question, Alex, is he says, where do we get QRobot desired? Don't think of it as the solution to the problem. I think of it as just something to say, when all of your when all the other things are equal, prefer to be in this comfortable position of the robot. So for my humanoid, it's my Q nominal. I just sort of said like this, reach out, do all the things you need to do, but Q desired robot or Q nominal is just the sort of the comfortable position, like the one that's on the screen for the EWA, right? So satisfy all the constraints, but it's a way for me to say, for instance, I'd like the elbow to be bent this way and not the other way, because there's two solutions.
I guess what I don't understand about this optimization method is like, okay, it makes sense to me if you like want to be in like one position, having an optimization problem, like what should your joint angles be? But like first, if you're doing like a whole trajectory, like I feel like I fundamentally missed somewhere how that works when I think of inverse kinematics as like you have one point, what should your joint angles be?
Yeah. So the simplest case would be I'm actually going to solve many IK problems independently, right? And they're going to find many joint angles. The reason that you would not just find all of them at the initial condition and all of them at the final condition is that you have to somehow, in the trajectory optimization case, find a path that will get all the way there. So between Q0 and Q1, it's a really deep question actually, right? So between Q0 and Q1 by itself might be only constrained minimally, like don't be in collision, but I don't care where you are in space that much. But by virtue of having to be related to Q2 and Q0 and through the chain, it eventually has to get to the goal. That's going to pull these intermediate IK solutions away from the comfortable nominal position and into some intermediate state that will ultimately have connectivity all the way to the end.
So you have predefined, wait, so I still don't understand where these points come from. You say like a Q0 and Q1, Q2, Q3. Yeah. Like,
imagine I was solving a single IK problem and I just had, so like for Q14, something in the middle, right? But I added an objective which said I need to be near this point in space and near this point in space. Okay.
Okay.
Right. That would be a reason to be somewhere in the middle of my optimization. So if I'm highlighting here, if this is Q14, right? There's some other point in space here that I need to be near. There's some other point in space here, and that's why Q14 lands here instead of like back at the initial conditions.
Oh, okay.
So, well, no, but I haven't. So I don't actually write that constraint. What I say is that Q1 must be related to Q0 and Q2. Q2 must be related to Q1 and Q3, right? The only hard constraints are that Q0 is at the origin and Q final is in the goal. But through the chain in order to satisfy all those constraints, it must spread the points out through those intermediate solutions. It's the only way it can solve the problem.
Okay, this makes way more sense now. Thank you.
No, that's great. I'm glad you asked.
For each IK solution to be independent, does that mean that multiple solutions are? How do you account for multiple solutions if each IK problem is independent?
Good. So in the sample-based case,
yeah,
I probably would not put the Q0 objective. I would have an unconstrained. I would basically. I say solving an IK problem in the sample-based planning. That's probably where I confuse people. I would only check the feasibility I would only check whether the constraints are satisfied or not. So I would sample a point at random, right? I would ask, are my constraints violated, true or false? And I would completely ignore any objective. And I would keep the point if the constraints are satisfied. And I would discard it if they're not satisfied. Okay, so that's going to give me a bunch of points here, but with unspecified objective. And then only after, and I make a connectivity to say, is this close enough here to be able to be willing to consider a possible connection there? And then the objective function, the same thing that was just happening in the trajectory optimization, getting pulled across, happens in the step where I'm solving, we've decoupled that, right? So it's in this second step where I'm solving a shortest path problem on the graph that it's actually doing effectively the optimization part that we did in the first problem. Okay, and when we solve the IK problems independently, there is no constraint pulling them during the sampling time. It's actually, so it's atypical to say that even in sampling based methods, you'd be solving a small IK problem. I have a reason that I was advocating for that, and that I'll tell you in a second. But I'm sorry, maybe that confused things, right? So most people would just say, sample uniformly, completely, don't even think about it solving an IK problem at all. Just sample cues, check if your robot is in collision, keep it if it's not, okay? I wanted you to think about this as a richer, because you can add other constraints like joint limits and other things to this. And in particular, there are some things like our hand wanting to be on the cylinder exactly would be, if our goal is a lower dimensional object, then you will never sample from it, right? So the ability to have a small inverse kinematics problem be your sampling strategy can allow you to solve some of these problems that would be impossible to solve with sampling alone. Thank you for asking. I'm sorry if I confused you with that. So the question is, when you're solving the shortest path problem, how do you make sure that the edges are viable? When you're adding them to the roadmap, every time I sample this point, I find its neighbors, and before adding the edge to the graph, I will like Rebecca was asking before too, I will sample many points along this, check collisions for all of them, and only add the edge in the first place. So we do that at the roadmap creation time, because having less edges will be a more efficient search later. Having less nodes really helps a lot.
So is there some like assumption, like context dependent assumption on like regularity? Because it's at some point you have to find some like discretization at which you sample to check for collisions.
Yeah, it's always approximate there, except for people who try to do things like this, the bounding boxes, the convex hull collision geometries. But typically, philosophically, I think sampling along one dimension, you can do it arbitrarily finely. This is not the place where like all the high dimensional geometry stuff gets you. You can sort of sample enough and be pretty happy. And with very low probability, you will have violated that.
Thanks.
Sometimes people will just make their collision geometry a little conservative too. I think you can, based on the gap of your sampling, you can add a little bit of geometry to your objects, and that'll also give you some guarantees. But conservative makes you more conservative. Cool. Okay. Thank you for the questions. So I do think, okay, to play my cards here, I actually think, say this carefully, I don't think sampling is naive, but sort of. I mean, like it's kind of crazy. Like if we really understood the problem, then you wouldn't think that just sampling in the uniform distribution would be the right solution, right? Oh, good. Yeah. So Dale's pointing out that you can parallelize those collision checks too. But the fact that we're sort of solving these problems by random sampling, sometimes randomized algorithms are justified and very good, and this is definitely one of the success stories. But it kind of feels like we haven't understood the problem if we have to result to sampling. So I actually think for finding individual samples, especially in more complicated geometry, then doing a little bit of, if I got a sample in here, do a little bit of gradient descent, a little optimization-based things to get me out of collision to find a sample, especially when you have constraints that are lower dimensional, like living on this, I'm grabbing the ball or something like this. Adding a little optimization in your sampling step can make a lot of sense, okay? But I also think there's something broken about the way we write the trajectory optimizations. And I think this about all forms of trajectory optimization, which is the fact that we've preordained the dimension of X and haven't, it's very nice to separate out the sampling step and the map generation with the optimization step. You don't, I think in these problems, you don't pay a huge price from separating those two. And that's exploiting something specific about this problem that generic optimization, like if I just tell my SNOPT algorithm that I've got this many decision variables, it has no way of understanding that problem specific structure. So I think the sample-based planners are extremely good, but maybe not because they're sampling. Somehow because they've written the problem in a more clever way. I wouldn't be surprised if we had related algorithms in a handful of years that used sampling less but still reaped a lot of the benefits. Okay, there are other differences too. The super big one is for the sample-based planners is probabilistic completeness. Okay, so if a trajectory exists, a path exists that satisfies my constraints, I will eventually find it. With probability 1, as number of samples goes to infinity. So you could argue that that's a weak thing to say, and actually it is sort of like simple algorithms that don't work well can have that property, but it's super nice to know that if I run this longer, it's going to solve even very hard problems. In practice, the thing you don't ever get from a probabilistic completeness versus a complete planner is that you never know that a problem is infeasible, right? So if there actually is no path, then you don't know that you're done sampling. You might just have to sample more. Although you don't know that for the trajectory optimization either, so maybe that's not fair. I do think that what I started saying in response to Alex's question is you can combine some of the benefits. You can combine heuristics, optimization for sampling, etc., to improve the sample-based motion planning performance. That's a big one. It shouldn't scale to high dimensions. That's a weakness, but it's still surprising at how well it goes, how high it goes. And compared to the trajectory optimization, when I say trajectory optimization scales to thousands of dimensions, the trajectory optimization has to solve the problem for all of the dimension of that is the length of the path times the dimension of the configuration space. Whereas for motion planning, for the sample-based planning, it's really just the dimension of the configuration space. So it stays in a lower dimension. It will still crap out. It just high dimensional sampling doesn't work eventually, but it tends to solve even these small humanoid problems with joints pinned and the like. You tend to need post-processing. problem with having a randomized algorithm is you get a random trajectory out. There's a, you know, you'll recognize it if you see it. We call it the RRT dance, right? The robots that kind of, they go to pick something up and they go, you know, like sort of do these kind of things and eventually go pick it up, and it's good, but not optimal, right? So typically, but if you know both trajectory optimization and sample-based planning, and you've got both of them in your library, then you just do your sample-based planning when you think you need it, and then run trajectory optimization on that planner because it's already found a good solution, and you can use trajectory optimization to tune it up. Right? We have versions of it, for instance, that will do anytime optimization. So as soon as the RRT or the PRM is done planning, you'll start executing the trajectory. And as you're executing the trajectory, it'll continue to optimize the rest of it out, given those runtime constraints. So you get some of the best of both worlds. You don't pay the price of the trajectory optimization immediately, but you get increasingly good control trajectories out. The other really good one for the PRM world is the multi-query. I think that's actually a very big deal, especially if you're going to be moving around the same environment over and over and over again. You might as well just solve this big complicated roadmap once and use it lots and lots of times. You can do optimization. You saw them in the list of the OMPL solvers. Those are called, for instance, the ones that are famous from RRT or from MIT are the ones with the star after them, which is a way to basically, as you're adding edges, if you've added a node that is, if I go back to this picture, if I were to add an edge here, I can connect to its neighbors and actually delete some of the connections to rewire so that I only keep the most efficient connections. And a simple algorithm like that can actually make you slowly optimize your objective. In practice, I think a lot of people don't know if it's worth the time to let the optimization run, certainly not for single query kind of planning. Okay, so I know I got to finish up here. Real-time robotics is cool. RT is cool. James is cool. I had some other cool thing at the end here. Oh yeah, just to end again, I feel like we're living in this space when we talk about these randomized motion planning algorithms, these collision-free motion planning. It's sort of like robots, and Charlie's actually saying it. I guess I have the audio off on mine, which would make sense. But if you ever, I would recommend you actually put the audio on. But he's talking about, oh, robots move through the world and they're afraid to touch the world. And he was using a soft skin to just sort of push through and understand when the robot can continue to make progress, even if it's in collision. And I think that is going to be big. I don't know. I think robots will have skin at some point, and you shouldn't be afraid of contact. And we're living in this world where if we're solving these super complicated geometric puzzles, I don't know, it's a little too much. I think you can do it. Peng, who some of you know Peng in our lab here. Let me forward since we're out of time here, but he's been working on just using the internal torque sensing of the KUKA to try to estimate the contact locations well enough that you could basically do the same thing that the robot with skin did, but with no extra sensing. And there's cases where it works beautifully, and you can just keep moving and react to the unexpected collisions just fine. But there are also some fundamental limitations to that the identifiability of the forces is limited because of, you basically, like if you had a force directly on the along an axis of a joint, you just can't measure it basically. But there's nice work on sort of understanding what you can and cannot do in that space. Cool, okay. Let me finish up here. Ask you for your feedback on what you want to do for the remaining lectures. Anything else you want to ask us about projects or anything. I'm actually, again, willing to stay on for a bit here if anybody wants to ask questions now about projects, and we're going to do a project week next week. I hope everybody knows that. So I'm going to send out or one of us will send out a schedule where people can fill in during lecture time or some other times sprinkled throughout the week. There'll be a big menu for you to pick from, and we'd like each project team to sign up for a slot. We'll send the details in on Piazza. Okay. I'll just hang out here, but
I had a question.
Yeah.
So if you wanted to use RRT for motion planning, but you had like an idea of some pretty good but non-feasible trajectory to start with. So say you, I don't know, use like quaternion slopes to get from point A to point B, but you like very slightly intersect a constraint. Can you seed your initial tree with points from that path and then maybe plan more efficiently?
yeah. So I think certainly trajectory optimization improves from an initial guess, but you can imagine if the initial tree for an RRT has points, then when I sample it randomly in space, it will more likely connect to my existing tree. It'll pull itself out of collision. So it does have that sort of warm starting property also. It doesn't do like targeted, the naive sampler doesn't do targeted sampling at the places where you're in violation of constraint. So you might grow your tree, in places where you don't need to. You might eventually grow it, but then you'll eventually grow it where you need it to.
Mm-hmm.
And there are a lot of people have proposed heuristics which try to adapt the sampling distribution so that it can, target the most important places.
So we could use something like stuff we did earlier in the class, then I guess a probabilistic sampler, and then trajectory optimization to create maybe like a really good pipeline for generating the trajectory.
Yep. I think trajectory optimization works for a large class of problems, and I think if you're outside that class and you're getting you're failing with your trajectory optimization, then you can do sample-based planning to find a solution and follow it up with trajectory optimization, and that actually is a pretty darn good pipeline. Like people make companies on that pipeline. So even without the full trajectory, a lot of people will just smooth, like with a much simpler smoothing algorithm, the output of the trajectory of the RRT kind of planners, and not implement a full trajectory optimization pipeline, and that still works too.
Will they take like the fixed knots from RRT and then smooth it with